And what you're seeing here is that the sum of potential energy at point B and the kinetic energy at point B is the same as the potential energy at A and the kinetic energy at point A. One can be converted into the other, and it can be converted back. Kinetic energy can be converted back to potential energy, and potential energy can be converted back. But the sum of them, which we call mechanical energy, is conserved. And mechanical energy is only conserved if the force is a conservative force. It's extremely useful. We will use it many times, but you have to be very careful. It's a dangerous tool because it's only true when the force is conservative. Spring forces are also conservative. But, for instance, friction is not a conservative force. If I move an object from here to here, let's suppose I move this object, and I go along a straight line, then the friction is doing negative work, I am doing positive work. But now suppose I go from here to here through this routing. You can see that the work I have to do is much more. Friction is not a conservative force. The frictional force remains constant, dependent on the friction. The kinetic friction coefficient is always the same, the frictional force, which I have to overcome as I move. And so if I go all the way here and then all the way back to this point where I want it to be, then I have done a lot more work than if I go along the shortest distance. So friction is a classic example of a force that is not conservative. If I look at this result, the sum of gravitational potential energy and kinetic energy is conserved for gravitational force, then it is immediately obvious where we put the zero of kinetic energy. The zero of kinetic energy is when the object has no velocity, because kinetic energy equals 1/2 mv squared. So if the object has no velocity, then there is no kinetic energy. How about potential energy? Well, you will say, sure, potential energy must be zero when y is zero, because that's the way that we defined it. You see, mgy is gravitational potential energy. So you would think that u is zero when y is zero. Not an unreasonable thing to think. But where is y is zero? Is y zero at the surface of the Earth? Or is y zero at the floor of 26100? Or is y zero here? Or is y zero the roof? Well, you are completely free to choose where you put u equals zero. It doesn't matter. As long as point A and point B are close enough together that the gravitational acceleration, g, is very closely the same for both points. The only thing what matters then is how far they are separated vertically. The only thing that matters is that ub minus ua, ub minus ua would be mgh. It is only the h that matters. And so you can then simply choose u0 anywhere you want to. It's easy to see. Suppose I have here point A and I have here point B. And suppose this separation was h. Well, if you prefer to call zero potential energy at A, I have no problems with that. So we can call this u equals 0 here. Then you would have to call this u, you have to call it plus mgh. If you say, no, I don't want to do that, I want to call this 0, that's fine. Then this becomes minus mgh. If you prefer to call this 0, that's fine too. Then this will have a positive gravitational potential energy, and this will have one that is higher than this one by this amount. If you say, really, I like to call this 0, of course the same holds. What matters is what the difference between potential energy is. That is what we need when we apply the conservation of mechanical energy. That is what we need in order to evaluate how the object changes its kinetic energy. So where you choose u0 is completely up to you. I have here a pendulum. I have an object that weighs 15 kilograms and I can lift it up 1 meter, which I have done now. That means I've done work. mgh is the work I have done, believe me. I've increased the potential energy of this object. 15 times 10 is about 150 joules. If I let it fall, then that will be converted to kinetic energy. If I would let it swing from 1 meter height, and you would be there and it would hit you, you'd be dead. 150 joules is enough to kill you. They use these devices, they're called a wrecker ball. They use them to demolish buildings. You lift up a very heavy object, even heavier than this, and then you let it go, you swing it, thereby converting gravitational potential energy into kinetic energy, and that way you can demolish a building. You just let it hit, and it breaks a building. And that's the whole idea of wrecking. So you are using then the conversion of gravitational potential energy to kinetic energy. Now, I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive. See you Wednesday.